So this video is the first of a couple of videos where we'll go over applications of our first order ODE. And in our standard form, we'll write that as y prime plus p of x, y is equal to f of x. And as we apply these applications, we're going to change some variables here. So I hope that doesn't lead to too much confusion. So in our first application, let's consider a slope. We're going to consider a mass on a slope. And this mass, we could, it could be you on a bicycle, for example. And so it's a rectangular U, I guess. And it has a mass m, and it's on a slope, on a hill slope, or if it's a go-kart, it's a ramp or something. And that it slopes at an angle theta from horizontal. So if we look at the forces on this mass, U on a bicycle, we have, first of all, we have the force, the pulling force of gravity, the downhill pulling force of gravity, which is proportional to the mass. It's proportional to the acceleration of gravity, g, and proportional to theta, sine theta. So here we have m being the mass, g being 9.8 meters per second squared, the acceleration of gravity, and then we have our angle theta. So that's one force that's pulling it downhill. And of course, as theta gets greater, sine theta gets greater, so that downhill pulling force increases as well. And so if we have we have frictional resistance of our motion, and we'll call that so it acts in the direction opposite the velocity. And so let's call this frictional force F, and that's equal to minus some constant times V. So here, V is our downhill velocity, downhill speed. And C is our constant. And that represents, for example, the friction of the wheels as they're turning, or it could even represent wind resistance. But whatever this is, this frictional force is proportional to the downhill speed, and it acts in the opposite direction of the speed. So if we draw out a force balance equation, we'd use Newton's second law, so force equals mass times acceleration. And the right-hand side, mass times acceleration, is just the derivative of our speed with respect to t. That's the rate at which the velocity is increasing. And so what are our forces? Our forces are our frictional force, CV, plus our downhill gravitational pulling force. And so we can write this as a differential equation as m dv dt plus, I'm going to bring the CV to the other side, same side as the acceleration term. And then I'm going to leave everything that's independent, that doesn't depend on v, on the right-hand side. So that's mg sine theta. Or we can rewrite this again as dv dt plus cv equals c over m v is equal to g sine theta. I'm dividing both sides by m. And so you might, I hope you might recognize this as if we substitute v in for y and t in for x, then this is of the form of y prime plus p of x, which in this case it's just a constant. C over m is a constant, but that's the coefficient on our dependent variable. And then we have a forcing function, which in general depends on x or t, but in this case it's just a constant. And so again, this is our forcing. I'm calling this a forcing function because it's the force that drives any motion, in this case v. So this is I'm writing this in the general form, so we can solve it using the method that we discussed. Okay, so let's solve our equation of motion, and therefore solve how v depends on t. So the first step, okay, is to solve the homogeneous equation. To solve the homogeneous part of the solution. So the homogeneous equation has zero forcing function. The part that is independent of v is on the right hand side, and we'll set that equal to 0. In this case it's a constant, which we'll set to 0. And we can solve this by separation, so we'll just keep the derivative term on the left hand side, and I'm moving this to the right hand side, so we have a minus c over m and then dt. So I've divided both sides of the equation by v and multiplied both sides by dt, and I've moved this term to the right hand side. And so if we integrate this, we get the log of the absolute value of v is equal to minus c over m times t plus some constant. I'll make that constant b, for example. And then this gives v is equal to some constant. We'll call that a, equal to, a times e to the minus c over m t. And so this is the first part of our solution. The form of our homogeneous solution will be an exponential decay function with time. So now to solve the non-homogeneous part, we allow a to vary. A to vary as a function of t. So we say that v is equal to a as a function of t, e to the minus c over m t. And we plug that back into our original equation. Plug that back into here. And so v prime dv dt is equal to, we take the derivative of the first term times the second. So we're now we're working on this first term of the equation. And so dv dt is first the derivative of a with respect to t, a prime, times the second term plus a as a function of t times the derivative of the second, which is minus c over m e to the minus c over m t. So this part is dv dt. And then we simply add on c. We have to add this term into the equation. That's c over m times v, which is a e to the minus c over m t. And that's all equal to our right-hand side, g sine theta. And as always, when we apply this method, you'll see that these two terms cancel. And therefore, we are left with a prime, e to the minus c over mt, is equal to g sine theta. And we can solve this. This is now the derivative of a with respect to t. So that means a prime is equal to g sine theta e to the positive c over mt. I'm dividing both sides by e to the minus c over mt. So from here, why don't you go ahead and stop the video and solve for A and then solve for V. And there, I'm going to continue to work on this, and you can check your work after you return. So I've integrated here, and I'm going to we have to add our integration constant, and I'll call that integration constant V1. So this tells us that our velocity, remember, is equal to A as a function of t, which is this, that's A as a function of t, times e to the minus c over mt, and therefore v is equal to v1 e to the minus c over mt. That was our homogeneous solution, as we showed derived originally. And then the part that accounts for the non-zero right-hand side becomes mg over c, not s. And these exponent terms cancel out. When we multiply e to the positive c over mt times e to the minus c over mt, we get 0, e to the 0 power, and so that gives us a 1. And this gives us plus mg over c sine theta. And that is our solution for our equation of motion of a mass on an inclined plane being pulled downhill by gravity and being resisted by a frictional force proportional to its velocity. Okay, so now we have a mathematical expression. Let's gain some insight for the behavior of our system. This is ultimately what we want to do. We want to understand the behavior of our system from a physical standpoint. So let me move this over here. So we can talk about it. And the first thing we need to do is, if we want to talk about a real situation, we have to solve for the situation that we want to describe. And so this requires an initial condition. And let's say you're on a bicycle, so we'll start you on a bicycle, and you'll just start from a standstill with 0 velocity, and then you're just going to release your brakes and let yourself go down the hill. And so in that case, our initial condition is v at time is equal to 0 is equal to 0. And so to solve for that particular situation, we need to solve for v1 that satisfies this condition. So to do that, we substitute v of 0 is equal to 0, and that's equal to v1, and we substitute 0 for time, and that gives e to the 0 power gives a 1, and then we add our forcing term. And when we solve for V1, we get V1 is equal to minus mg over c sine theta. And our particular solution, V of t, becomes V1, which is minus mg over c sine theta, e to the minus c over mt, plus mg over c sine theta. So this is our particular solution for that particular initial condition. And so let's sketch this and see if we can gain some intuition for what this is telling us. So here's the time axis, t, and this is our speed axis, v. And again, at time is equal to 0, we start off with 0 speed at t is equal to 0, right? So this is our starting point. And as you might be able to see that, well, actually, so that's when t is equal to 0. When t is infinity, when t is really large, then we're raising this to a very e to the minus large number. So that makes this term equal to 0. And we get a velocity at time is equal to infinity of mg over c sine theta. And this exponential decay function, it's an upside down exponential decay function, makes the velocity rise to that terminal velocity. This is our terminal velocity, or terminal speed. So you start off at rest with your feet on the ground, take your feet off the ground, and you start rolling down the hill. And initially you're accelerating down the hill at the greatest rate, and as you accelerate and your speed increases, the resistive frictional force also increases, so your velocity starts to level off until eventually you reach your terminal speed going down the hill. You're not going to go any faster than this unless you start pedaling or turn on your e-engine or something on your e-bike. Let's look at this in just a little more detail to close off. I'm going to write down our force balance equation again. And remember, very close to our starting point here, v is about equal to 0. It's very small. It's approaching 0. So right here, we have a balance. Our acceleration is exactly equals the downhill pulling force due to gravity. So this is where our acceleration is maximal. And that contrasts with this point here, where if we write our force balance equation, here we have an exact balance between our air resistance, our frictional force, our resistance of our wheels in the wind, and that's resisting the downhill pulling force. And so here, this is equal to 0. At large time, the acceleration is near 0, and so that's why we are at our terminal speed. Okay, so this is our first example of our application of our linear first order ODE. We're going to build on this particular example excuse me, as we look at higher order and slightly more complicated differential equations.